This is further stats 1 from 2019. So first question looks like a binomial being given a probability of 0.02. We've gone in as 40 and we're looking to get 3 of them. Now we could get more than 3 of them, right? So we're actually looking for probability of more than or equal to 3, greater than or equal to 3, which is of course the same as 1 minus probability of less than or equal to 2. We can put this in a calculator with the binomial cumulative function. We'll get this, which turns out to then be this. Barney intends to buy one at a time until he claims the prize. So he's looking to get 3 of them and he'll stop once he's bought 3. That's a negative binomial distribution. And we can see the probability that x equals x, and we're looking to have this done by the 40th, is given here. We can just use this form here. X is 40, R is 3, and we can just shove those results in here. P, of course, is still 0.02. So we'll put all of that in here, and we'll get this answer here. Find the expected number of bars he must buy. Well, this is just the mean, right? And the mean is given to us. It's R over P. R is still 3. P is still 0.02. And we'll have our answer straight away. Question number 2 then is a Poisson question because we've got an average of this amount per some period of time. Now, their time here changes to a 20-minute period. So there are 3 lots of 20 minutes an hour, times by 4 is 12 lots of 20 minutes in this period. So 80 divided by 12 gives us essentially our mean for our 20-minute period. So we'll do a Poisson distribution with 20 over 3, and we want the probability of more than 4. That's, of course, 1 minus the probability of less than or equal to 4. And we'll do a Poisson distribution, Poisson commutative calculator thing. We'll do this, we'll get this number here. That turns out to be that. So they're allowed 20-minute breaks each, and they can break this up into how many 5-minute periods they want. Now, first we're looking for, they're going to break their 20-minute break into 4 5-minute periods. So first we need to set up another Poisson distribution and find out what the probability is of not receiving a call in one of those 5-minute periods. So let's do, how many 5-minute periods are there in 4 hours? Well, there are 12 lots in 1 hour, times by 4 is 48. So this is the lambda we'll use for our new Poisson distribution. And if we set x to be 0, we're looking for, we don't want any calls in the 5-minute time. So what's the probability of getting no calls in this 5-minute distribution here? Well, it's that. And now we want that to happen 3 times out of 4. So we want this to happen 3 times, and we want not this, which is of course just 1 minus this, to happen 1 time. And that one event can happen at any one of the 4. So this is actually a binomial now. We can do 4 choose 1. We can have this happen 3 times and not this to happen 1 time. And we'll type this into a calculator and we'll get this here. On another occasion, she broke the breaks up, or they broke the breaks up into 1 5-minute and 1 15. So what's the probability of getting exactly 1 call in the 5 minutes? Well, it's just this distribution with x equals 1. Again, just put in the calculator, we'll get this. And what about 15 minutes? Well, one more time. How many 15 minutes are in 4 hours? 15 times 4 is 60, times another 4 is 4 hours, so that's going to be 16. So we're going to do 80 divided by 16, which is 5. So we're going to do a Poisson distribution with lambda of 5. And we'll just look for probability equals exactly 1. Again, using a calculator, and we'll get this. This is the Poisson PD function, by the way. And we'll get this because it's equal to. And then we just need to do, we want both these things to happen, so it's this times this, and we'll have our answer there. Question number 3 then is about a spinner with probability this. Spun 80 times, let's do 80 times this to work out the expected numbers. So 80 times that, and so on. We'll get all of these. And now find an estimate of probability the main will be greater than this. What I'm first going to do is find the expected value of x, which is 1 times 24, plus 2 times 8, plus 3 times 16, and so on, all divided by 80. We'll do this again, actually, later on in the paper in a much more particular way. But anyway, for now, we've got this, which is 3. Of course, you could have got that just by noticing the symmetry in this question. Notice all the symmetry from this line downwards. So, of course, the answer is 3, but I didn't notice that at the time. So anyway, I'll also work out e of x squared. Now, the reason I'm going to do that, which is, of course, 1 squared times this, plus 2 squared times this, plus 3 squared times this, and so on. The reason I'm going to do that is because I can use this formula here. They've asked me for variance, which is actually spelled with an A, but I don't really care. They've asked me for variance. If I hadn't pointed that out, no one would have noticed that as well. So I'm a bit annoyed that I actually pointed that out. We're going to do e of x squared minus e of x all squared. So this minus this squared, which is just 2.6. And the reason that's helpful is because what I want to do is I want to use the central limit theorem here. And the central limit theorem says that anything can be, any sample can be taken as a normal distribution with your mean here and your variance over n here. So we've already worked out this is 2.6, n is 80, and the mean is 3. So you've got this normal distribution here. This is just 2.6 over 80. And we're looking for the probability of this being greater than 3.25, which is the same as 1 minus less than or equal to 3.25. And we can just put this into a binomial CD function in the calculator. Just remember, you're going to use lower, like minus 100 maybe, upper 3.25. Mean is this, and then your standard deviation or your sigma is sorry, your sigma is going to be this square rooted, because normally you'd write 3 comma something squared. So we're going to square root this to get that something, and we'll end up with this number here when we type that in, and we'll get this here. Good. Question number 4 then is about trees and a wood. These two people divide the woodland into 80 equal squares and record the number of trees in each, and you get this table here. Liam believes they're deliberately planted with 6 per square and a proportion p that have survived. So this looks like a binomial. They planted 6 and p of them are still alive. So that's going to be an x sort of binomial with 6 comma p. And suggest the model Liam could use to describe. Oh, sorry, I just did that. So Liam decides whether to test this is suitable or not, given this here. So we need to do a few things to start off. Firstly, this column needs to be collapsed in here because this is less than 5. Sorry, just describe what x is, I guess, is what I should have said. So x is the number of all x degrees in the square. So collapse this column into here. So this is now 5 and 6, and this plus this is that. And also that means, now this isn't less than 5, it's kind of irrelevant though, but we don't want to collapse this. Sorry, we do want to collapse this because this has already been collapsed. So we do also have to collapse that and say this is 5 and 6 and it's 18. Obviously this is irrelevant because there's 0 of them anyway, and it's not in this table, so that's irrelevant anyway. And also, this has notice been collapsed here for us already, so we're going to have to collapse this as well to make it a 5, because otherwise when you're doing this formula here, if you don't have the same number of columns to match, then this just isn't going to work at all. So what I'm going to do is I'm going to do this one squared over this, plus this squared over this, plus this squared over this, plus and so on. And so I need the columns to match, and then I'll just take away n, which is 80, and we'll get this here. And then what we need to do is look for the chi-squared value that corresponds here. So 0.05 is what we'll look for here. Degrees of freedom. Now, V, it's not actually called V, but I call it V anyway. 1, 2, 3, 4, 5 columns and 2 restrictions. There's one restriction because these have to add up to 80. And there's another restriction because he's calculated these expected frequencies. There's a note in the textbook that says if these expected frequencies are, if there's a calculation being done to get these, that's a restriction. If it's just guessed using an estimate that seems sensible, then that's not. But these have been calculated. So if you see the word calculated, that means extra degree, extra restriction, and therefore 5 minus 2 is 3. And so we'll look in the chi tables, and we'll end up with 3 here, 0.05 over here. We'll take that box there, and that is actually less than the one that we got here. So we're within the critical region, and therefore we'll reject the model and say it's not suitable. Simone does something different. She uses a Poisson distribution to get these expected frequencies. Notice she calculates, so that's going to be restriction later on. She calculates these, work out S and T. So essentially what we're being asked to do here is figure out the lambda that she used to calculate these using her Poisson distribution. So what we can say is, well, when you're doing a Poisson distribution, lambda is just the expected value. It's just the mean. So if we work out the mean of this, we should get her lambda. So 0 times 1 plus 1 times 4 plus and so on. All divided by 80, and we'll get this. So that must be our lambda. That must be our expected. That's our lambda there, so we'll use this. You can double check that that works for these if you want to. Otherwise, just shove in, look for the expected value to get 3. Just use a calculator, we'll get this. And then for 5, get this. We, of course, have to times those probabilities by 80 to get actually the expected frequency. So times it by 80 to get S and T. And we end up with these two results here. Write down a hypothesis. So H0, I guess, is Poisson is suitable. H1 is that it's not. So fine. Test statistic for this is this. So that's the x squared value that we worked out using OI squared over E minus N and so on. But they've already done that for us. So now we just need to complete it. So we need to say, firstly, degrees of freedom. We've got 5 columns. No, we haven't. We've got 6 columns. 1, 2, 3, 4, 5, 6. Take away 2 because they have to add up to 80 and because she did some calculation. So that gives us 4. The table's at 4 here with 0.05 is this number here. And our value, or the value they've given us, is less than that, so we're not in the critical region, and therefore it seems like a suitable model. Using the results of both these tests, explain whether this is likely cultivated or wild. Now, so the Poisson passed the test, and we just said that that was suitable. The binomial didn't. Now, the Poisson is inherently random in what it does, right? It's just working out. That's kind of what it's about. And it was a suitable fit, according to our maths, so therefore that suggests that the woodland is wild, because Poisson is inherently random in that respect as well. Binomial isn't. Binomial is sort of more deliberately done. And the binomial didn't fit the woodland. So therefore we've got 2 pieces of evidence that the woodland is likely wild, I guess, is what they wanted us to say. Question number 5 is about this bypass. We've got a Poisson distribution with mean of this. So a hypothesis H0, I guess, is that the lambda is 2.5, and now it wants to test one that's a change. So this is a two-tailed test, and H1 will be lambda is not equal to 2.5. And we'll look for a 0.025 level of significance because it's two-tailed. So okay, now once you've done that, find the critical region. So I find it's best just to, firstly, X is the number of accidents in 3 months. Now they've given us a 1 month thing here. So we'll just times this by 3 to do our distribution with 7.5 instead. So that's fine. I find it easiest to just get out the table. So look for 7.5 and find the number that's below 0.025. Again, it's a two-tailed test. And that's going to be this one here, which is X less than or equal to 2. So one critical region is X is less than or equal to 2 because that's below 0.025. And at the other end, we've got 13 makes this greater, sorry, less than or equal to 13 makes that. So therefore, 1 minus that, we get probability of X greater or equal to 14 is 1 minus this, which is lower than 0.025. So therefore, X greater than or equal to 14 is the other end of our critical region. So we have this and this. Type 1 error is just this value here that you found for the low end plus this value here, which gives us this. Data from a series of 3-month periods are recorded for 2 years. Find the probability that at least two of these gives a significant result. Probability at least two of those. Oh, sorry, I'm doing the right thing. So this is I thought I was about to do the wrong thing. This is a binomial, right, in the middle of a Poisson question. So at least two in a 3-month period. So how many 3-month periods are there in 2 years? Well, there's 4 3-month periods in a year, times 2 is 8. So this is a binomial with 8 things to choose from, because there are 8 3-month periods, each with this probability of giving a significant result. And we want to find the probability of at least 2, so P of y, I guess, being bigger than or equal to 2, which is, of course, 1 minus probability being less than or equal to 1. And of course, we can just do that in a binomial commutative function in our calculator, and we'll get this here, which is this here. Given the number of accidents per month in the bypass is actually this, find the type 2 error. Type 2 error is the probability that you accept H0 when it's wrong. So the probability of accepting H0, well, we accepted H0 if we were less than or equal to 13 and greater than or equal to 3. So that was where we accepted H0. But given that H0 is wrong, means that lambda is actually going to be this value, times up by 3, because that's per month, and we've got a 3-month window here, is going to be 6.3. So what's the probability of this given this? Well, we just have to find this given this distribution. So this, of course, is probability less than or equal to 13 minus probability less than or equal to 2, just taking away the first couple of values. So okay, we just type this in the calculator, we get this and this, and then we take them away, and we get that there. Question 6 is the probability generating function then. Firstly, the key result here is that gx of 1 equals 1. You'll always have to use this in your papers, so always know this. Put in t as 1, and we're expecting 1 here. 2 over this is just 1, it's just 2. So 1 divided by log 2 is k, therefore. So we get this. Now variance, this is in the formula book, so just know that this is in the book here for these functions here. So we need to work out g dashed and g double dashed. So here, what I did here was I said, okay, this is actually this log 2 over 2 minus t is actually just log 2 minus log 2 minus t. So I think we just get this. And now, of course, I can differentiate this because this is just a constant, so it goes away. So if I expand this out, I get minus k log of this. And now when you differentiate a log, the inside of the log goes below in the fraction. And the derivative of the inside goes at the top. Now the derivative of this is minus 1, which will cancel with this minus 1, and I'll just get k times this here. And then, of course, I can derive that again. This is 2 minus t to the power minus 1. The minus 1 comes down, becomes a minus 2. And then by chain rule, the derivative of this is minus 1, which cancels with that minus 1, and we just end up with this. Evaluate both of those things at 1, and we get just k both times, which is really nice. K, of course, is 1 over log 2. And so, therefore, the variance of x is this one plus this one minus this one squared. And those come together, and I decided that that was all the simplifying that I really needed to do. Last question is the most interesting thing here. Find the probability that x equals 3. Now, that's the coefficient of t cubed in the probability generating function. Now, the problem here is that our probability generating function is not a polynomial. So we don't have a coefficient of t cubed. But we can fix that by using a Taylor series. This is the first one they give you, this Maclaurin series here, whereby, I mean, we're using f of t. This is just f of t here. But f of t is equal to f evaluated at 0 plus x times f evaluated differentiated and evaluated at 0 plus x squared over 2 factorial f dash dash of 0 plus all the way to t to the r over r factorial. Now we're looking for t cubed. So we're going to be t cubed here is over 3 factorial, f differentiated 3 times and evaluated at 0. So let's differentiate this 3 times. Now we've already done it twice. And let's do it again. So the minus 2 comes to the front, becomes a minus 3, times by minus 1, and that cancels there, and we get this. Evaluate that as 0. 2 minus 0 is 2, to the power minus 3 is an eighth, times 2 is a quarter, so we get k over 4. And so that's k over 4. Divide by 3 factorial. 3 factorial is 6. K over 4 divided by 6 is k over 24. K is 1 over log 2, so that would be 1 over 24 log 2. And at this point, I'll just obligatory put on the meme here, which is that Maclaurin series are absolute rubbish and shouldn't have a name. They're just Taylor series evaluated at 0, and I don't understand why they got given a name or why anyone follows that procedure, but apparently they do. Question 7, a spinner can land on red or blue. Probability of 1/3 that it lands on blue. We're going to spin this until we get the first blue. Now that's a geometric distribution with probability 1/3. And we can look in the formula book and we have all the information here. The probability that x equals x, which is just this here, right, where x is b, I guess. I should have put a b here, but whatever. We just use p as 1/3, 1 minus b is 2/3, x is 4, so it's 2/3 to the power 3, and we end up with this, which is going to be that. Probability of b is less than root of 5. Now, there's a few ways you can do this. The first thing you do is just use this idea here, where you said probability less than root of 5 is probability of 0 plus probability of 1 plus 2 plus 3 plus 4 plus 5. And you could just use this formula 5 times and add up the results. Alternatively, you could use this idea, which is in the textbook but is not in the formula book, so you could memorize that. Or you could think this through logically. The probability of getting a blue within the first 5 rolls is just the probability of avoiding 5 reds in a row. So it's just 1 minus 5 reds is, well, a red is 2/3, so it's 1 minus 2/3 to the power 5, which is exactly what this formula would give you if you just put this into there, and you get this here. Find expected value of b squared. We're going to use the same formula we used much earlier on in the question, which is this. Now, expected value of b squared is there, so we need this and this, but that's fine because expected value of b is just the mean, which we have the formula for, and the variance we have the formula for. So p is 1/3 in both these, we'll just put that in. This makes 2/3, this makes 1/9. Dividing by a ninth is the same as dividing by 1/9 is the same as times by 9, so 2/3 times 9 is 18/3, which is 6. And then this is 1 over a ninth, which is just 9. And you add it together, you get this. And now, again, a really interesting question right at the end of this, which is Tamara can play the game. She can choose either red or blue. If she chooses blue, her score is x squared. Now, but we already know the value of the expected value of x squared or b squared. If you choose blue, it's 15. So we already know that bit. We know her expected score here is 15. Now, what about if she chooses red? So if she chooses red, then this is a geometric function with probability of 2/3 instead. So that's fine. And now, what's the expected value of e to the power x? Well, that's just this function here, e to the power x, times each of the probabilities for each x. So it's a bit like that table we saw earlier of like 1 times 2 plus whatever times this probability times all this. It's a bit like that, right? It's the same idea. We can just do that with any function we want. Now, of course, this here from the book we were looking at earlier is just this. That's this here, where probability again is 2/3. Let's put that in. And now this here is the sum. We're going to sum from x as 1 to start with, because of course the first time we can get a red is on the first roll. That's the earliest. So we're going to sum from x as 1 all the way to x infinity, because technically we could be here forever spinning this, because we could just never get a red. So we're going to sum from 1 to infinity this here. Now, if you actually write out the first few terms, you'll get this. Just put an x as 1, you'll get this. Put an x as 2, you get this. And this is just a geometric series, or sum, because we add in another 3, we times by e every time to get e1 to e2. And we also times by an extra 1/3. The 2/3 are doing it. So to get from this term to this term, we times by e over 3, I think, or e times a third, which is just e over 3. Now, e over 3, e is like 2.7, so e over 3 is less than 1, which means I think we can use this formula to sum this to infinity because the ratio is less than 1, or the size of it is less than 1. And the first term in our sequence is just this. So we can just say this infinite series is just this term divided by 1 minus e over 3. And this term is just 2/3 e, right? Because this goes away and this is just 1. So we get this. You can type that into calculator and get this. And because that value is bigger than this value, we're going to say that her expected score, if she chooses red, is bigger. So therefore, she should choose red. And that's the whole paper. Thanks for watching.